Okay, شباب, السلام عليكم. Inshallah, today we will continue in chapter 4. Last time we talked about the first law of thermodynamic, Q minus work is equal to delta U. And we have seen some application on first law of thermodynamic, how we can calculate the heat transfer and the work for any. And we have learned also how we can calculate this exchange of internal energy delta U in case if we have a steam or refrigerant. In this case, we will be using ZU. But in case if we have a gas in this case. In case when we have a gas, we said we'll be applying the equation, ideal gas equation, BV is equal to RT. Now, what if I need to calculate the exchange of internal energy in this case? Actually, in this case, the ideal gas equation does not relate to the change of the internal energy. So inshallah, today we will learn how to calculate the change of internal energy and the change of enthalpy in relation to what's called actually the specific heat in case if the working fluid is gas in this case. Type, let's start with the definition of specific heat and see how we can relate the change actually of internal energy and the change of enthalpy to the specific heat. So specific heat actually is a property of a substance, okay? This property actually is defined as the amount of heat added for 1 kilogram of a substance. So if we have 1 kilogram of a substance, let's say we have gas, 1 kilogram of gas. If we added actually this heat, some heat to this gas, and for a temperature rise, delta T is equal to 1 Kelvin or 1 degree C, it is the same. In this case, actually, this amount of heat added to 1 kilogram of the substance and result in 1 degree actually temperature rise, we call actually this heat as a specific heat. A specific heat is actually a property that is calculated in kilojoule per kilogram, kilojoule per kilogram Kelvin. If this heat added actually under constant volume, we call it actually CV, specific heat at constant volume. If this heat added to the system under constant pressure, we call this specific heat as CV. So this specific heat, shabab, is a measure actually of the energy storage capacity within a substance. Like here, if you look at this, the slide, here in the slide we have for iron to raise the temperature from 20 to 30 degrees C, we need to add heat about 4.5 kilojoule. But to raise actually the same temperature rise delta T for water, 1 kilogram of water, in this case we have to add more heat in this case, 41.8 kilojoule. That means water have actually higher heat capacity and it can absorb actually more heat for a small temperature rise. So water actually have higher specific heat capacity or energy capacity. It can store actually more energy in this case. But as we said, a specific heat, which is actually calculated or measured in kilojoule per kilogram, we said it is the amount of heat added to 1 kilogram of a substance and result actually in temperature rise of 1 Kelvin. We said if this heat added under constant volume, we call this is actually CV, the specific heat under constant volume, specific heat at constant volume. We call it CV. If this heat actually is added under constant pressure, actually as CV in this case. So both cases actually it is the amount of heat added and the result in 1 temperature rise for 1 kilogram of the substance. But usually, shabab, for we said CV, specific heat in general, is a CV or CV is a property of a substance. But for any substance, you will find actually the specific heat at constant pressure is greater than actually the specific heat at constant volume. Let's look here. We have an example here. Those values actually are for helium. If we have 1 kilogram of helium and we actually added heat in order to raise the temperature by 1 degree, in this case at constant volume, if the process at constant volume, we have rigid tank, the amount of heat will equal to 3.12 kilojoule in this case, which is the specific heat at constant volume, CV. For helium, if we have 1 kilogram of helium and we need to raise the temperature 1 degree C, but under constant pressure, so in this case, this piston will be moving in this case to keep the pressure constant. In this case, we have to add more heat to keep the pressure constant in this case. And this heat actually added under constant pressure, we call it as CV. But why usually CV is greater than CV? As you can see here from this example, if the system actually is rigid, we don't have actually change in volume, the volume is constant, then in this case, all of the heat added will be absorbed by the gas here, and it will result in this actually 1 degree temperature rise very fast. But if the system under constant pressure, then the piston is moving. So in this case, we have boundary work in this case. So part of the input heat in this case, added under constant pressure, will be converted to work, which is losses. That means we have to add more heat in order to have temperature rise of 1 degree C. And that's why the specific heat at constant pressure for the same substance is greater than CV. CV is greater than CV, because in case of constant pressure, part of the input heat to raise the temperature is converted or consumed actually to have boundary work due to the movement of the boundary. As I told you, for a closed system, the only way to have a constant pressure process is through the movement of the boundary, of the system. Okay? Let's see how we can calculate actually this specific heat at constant pressure and the specific heat at constant volume, and how we can relate actually the specific heat to the change of internal energy and the change of enthalpy. So let's consider a closed system. So first of all, we will be considering actually a closed system. This closed system, first of all, we'll consider the case when we have a constant volume closed system. And let's say here actually constant volume, that means we have a kind of rigid tank. And let's say actually we have kilogram of any gas in this case. Under constant volume inside there is this rigid tank. And we will be adding heat here. So some heat will be added to this 1 kilogram of gas. So in this case, if we are assuming adding a small amount of heat in this case, then we can apply the first law of thermodynamics in the specific differential form. Then we can say delta Q minus delta work will equal to delta U in this case. As this is actually a rigid tank, so we don't have movement of the boundary. So in this case, the boundary work is equal to 0, and we don't have any other kind of work. So delta Q will equal to delta U in this case. This is 1 kilogram of air, and by definition, the amount of heat added per 1 kilogram for delta T equal to 1 Kelvin is equal to the specific heat. This is constant volume, so this is a specific heat CV. So delta Q in this case will equal to CV if delta T here is equal to 1 degree C or 1 Kelvin. Okay? So delta Q will equal to CV, which is the amount of heat added with 1 kilogram to have delta T equal to 1. If we added more heat, then delta T is greater than 1. Then in this case, delta Q will equal to CV. We have to multiply by the delta T in this case. So delta Q is equal to CVT. Delta Q is equal to CVT, which is equal to the same as delta U. Okay? Or from this relation, we can say actually that the specific heat at constant volume is delta U by delta T at constant when the volume actually is constant in this case. And this is how we can relate CV with the change of internal energy delta U. So by definition, CV is equal to partial differentiation delta U by delta T when the process actually is at constant volume. Type U is a property. This internal energy is a property of a substance. Temperature also is a property. That means actually specific heat is also a property of a substance. Okay? This is the definition of the specific heat at constant volume. What about the case when we have constant pressure? The specific heat at constant pressure. Okay? So let's consider the same system. We have a closed system. But this closed system is undergo actually a constant pressure process, not constant volume. And we will be adding heat also. Then we can calculate in this case the specific heat at constant pressure. So step number 2, let's consider the closed system for actually constant pressure process. We said the only way to have a closed system undergo a constant pressure process is through the movement of the boundary. So in this case, the boundary is moving, and in this case, we have boundary work. And let's assume we have 1 kilogram of any gas, and we are also adding heat in this case. Okay, so we can apply the first law of thermodynamics. If actually a small heat is added, so it will be delta Q minus delta work will equal to delta U. This But in this case, we have boundary work. Delta work, which is boundary work, is equal to integration of BdV, or delta work will equal to BdV in this case. So we can say delta Q will equal to BdV plus BdV plus delta U in this case. Okay. But if we have temperature rise delta T, we add T, and delta T will equal to 1 Kelvin. Okay. I'm writing here 1 times 1 Kelvin or 1 degree C. This is actually the difference. It doesn't matter. Okay. So if we added heat and temperature raised actually by 1 degree, then in this case delta Q will equal to what? Delta Q will equal to Cp by definition, the amount of heat added per 1 kilogram to have delta T equal to 1. So delta Q will equal to Cp. But if we have added actually more heat and delta T actually raised more than 1, then in this case we have to multiply by delta T, or the temperature rise in this case. So delta Q is equal to Cp dt. By definition, we have enthalpy is the internal energy plus the flow energy, BV, U plus BV. Then we can say here what is it? We can say delta H, if we differentiate, so delta H will equal to delta U plus BV, it will equal to BdV plus VdV. Is that okay? But here the pressure is constant. The pressure in this case is constant. So dV will equal to 0. So this term VdV will equal to 0. Then delta H will equal to delta U plus BdV. So delta H will equal to delta U plus BdV. That means the right-hand side of this equation is equal to what? Delta H. And delta Q we have just calculated here. We have just defined, which is Cv dt. So we have Cv dt will equal to what? Will equal to delta H in this case. And by this, we can define the specific heat at constant pressure. So the specific heat at constant pressure, in this case Cv, by definition, it will equal to, so Cv, it will equal to just delta H divided by T, or partial differentiation dH by dt, but when the pressure is constant. Okay, and this is the definition of Cv. As we said, Cv is function of enthalpy, which is a property, temperature is a property. Then in this case, a specific heat actually also is a property of a substance. And this issue of Cv and Cv are function actually of pressure and temperature. Mainly it is function of the temperature, it is not constant. Let's see here in the slide, if we have 1 kilogram of air, to raise the temperature from 300 to 301, 1 degree Kelvin, then in this case, the specific heat, this is a rigid tank, this will be Cv. Cv will equal 2.718, the amount of heat we need to add for delta T equal to 1 Kelvin at 300 Kelvin, for 1 kilogram of air is equal to 0.718 kilojoule. If this air is at 1000 degree, then in this case to raise from 1000 to 1001, only delta T is equal to 1 also, but in this case we have to add more heat. Specific heat Cv will equal to 0.855 kilojoule. That means specific heat Cv and Cv are function of temperature, and they are raised actually with the temperature. Look here at the distribution. This is the specific heat as function of the temperature for different gases. So for any gas, the specific heat actually is raised in this case as function of the temperature. Okay, so it is not actually a fixed value. But in case this is a partial differentiation. So in case when we have an ideal gas, usually ideal gas is a gas under low pressure, or we can say the gas under low density or low pressure. So in this case, under low pressure, all gases actually act as an ideal gas. So in this case, gases actually become depending mainly on the temperature. All the properties of gases depends mainly on the temperature. When actually the case is under low pressure, this gas is existing under low pressure, or we can say it is an ideal gas. So for ideal gases, the properties actually of internal energy and enthalpy is mainly depending actually on the temperature. So in this case, for ideal gas, in case of ideal gas at low pressure, then in this case we can just say CV will equal to delta U divided by delta T. Or we can say, we can just remove the partial differentiation. Or we can say delta U will equal to CV delta T. Or by integration, if we integrate here, then we can say delta U, which is U2 minus U1, if we have any gas, undergo a process, let's say from state 1 to 2. So the change of internal energy for this gas, U2 minus U1, will equal to integration of CV. We said CV is function of temperature. As you can see here from this plot here, CV is mainly function of temperature. Usually it is second order function of temperature. So if we have CV as function of temperature, then we can do this integration from temperature T1 to T2, integration dt. Okay. This is the specific change of a specific internal energy. This is kilojoule per kilogram. This is CV is kilojoule per kilogram Kelvin. Okay, multiplied by delta T in Kelvin, so it will be kilojoule per kilogram. So delta U in this case is calculated. This is the specific value. To calculate the total value, you have to multiply by mass. Okay. Also like this, we can calculate delta H, which is the change of a specific enthalpy. H2 minus H1 will equal to integration of CB, which is function of temperature, integration actually dt from T1 up to T2. And this is actually how we can relate the change of internal energy and the change of enthalpy with as function actually of a specific heat at constant volume and the specific heat at constant temperature. So if you have this function CV as function of temperature, we can take this function and come here to this integration, do the integration, then we can calculate delta U for gases. Also, we can calculate delta H in this case. Based on this, we can calculate delta U and delta H for gases. But let's see actually the different ways when it comes to the application. How we can calculate delta U and delta H for gases. So calculations, we have different ways actually for the calculation of delta U and delta H in case of the working fluid is here. We said if the working fluid is a steam or refrigerant, we can just use the table to calculate delta U. But here actually, in case of gas, we have to relate actually to the specific heat. So calculations of delta U and delta H, but for gases. Okay, Shabab? So in this case, we are talking about gases. We have three main ways actually to calculate delta U and delta H. Let's say there is a problem. We have a gas. This gas undergo a process from state 1 to state 2, and we need to calculate delta U and delta H. So first of all, we have what we call actually the variable specific heat approach. The variable specific heat approach as well, we should CV and CV are function of temperature. So we assume actually the real case, CV and CV are function of the temperature. In this case, they have done already tested different gases under different temperature, pressure, volume, and every time they have measured the value of the internal energy, the change of internal energy, and the change of enthalpy in this case. And based on this, actually, they have listed those values of internal energy and enthalpy as function of temperature from table A17 to A25. Each table is representing actually the change of internal energy and enthalpy for a given gas as function of temperature in this case. And in this case, Shabab, to use those tables from A17 to A25, we need only one property, which is the temperature. As we said, in case of ideal gas under low pressure, the properties of gas becomes actually depending only on the temperature. So in this case, we don't need two properties to go to tables from A17 to A25. Just what we need is the temperature in this case. In table A17, this table look here is for air, and table A19 is for O2, and we have different table for carbon dioxide and different gases in this case. So depending on the working fluid in this case, we can just select the proper table, and in this case we can say the change of internal energy delta U will equal to U2 minus U1. U2 is calculated actually at temperature T2. U1 is just calculated actually at temperature T1, and those actually calculated actually from tables. The value actually of U2 and U1 are calculated from tables A17 to table A25 in this case. Table A17 is for air. So if we have a problem, we have the working fluid is air undergo process from 1 to 2. And actually following the variable specific heat analysis, we can just use actually say delta U will equal to U2 minus U1. And U2 and U1 are calculated at temperature T1 and T2 from table A17 in this case, which is the case of air. If it is oxygen, I will be using table A19 in this case. If you look at this table, you will find this is very important. Table A17, the value actually of this U2 and U1 are calculated actually in kilojoule per kilogram Kelvin. Okay, but starting from table A18, or yes, this is table A19. So starting from table A18 to A25, from A18 to table A25, you will find the value of U and H are given actually per kilomole, not per kilogram. So the values that is listed in the table from table A18 to A25, the value of internal energy and the enthalpy is given actually per kilomole, not per kilogram. Only the value in table A17 for air, the values here for enthalpy and the internal energy as function of temperature are given in kilojoule per kilogram. But for other table from A18 to A25, it is given per kilomole. So what should we do in this case? In this case, we can get at temperature T1, we can get the internal energy U1 per kilomole, and we can get also the enthalpy H. And to convert, in this case, we can just say the internal energy per kilogram equal to the internal energy per kilomole divided by the molecular weight. And like this, enthalpy per kilogram is equal to the enthalpy per kilomole divided by the molecular weight in this case. Okay? And molecular weight is coming from where? Depending on the working fluid, we can get this actually the molecular weight of any working fluid actually from table A1. Okay? So table A17 will give you the value directly in kilojoule per kilogram. But from A18 to A25, in this case, the value will be given actually in kilojoule per kilomole. Okay, so we have to convert it to kilojoule per kilogram by dividing by the molecular weight in this case. Okay, and the values listed on this table from A18 to A25, these are based actually on the experiment. So those are actually the most accurate value. Those are the most accurate value in this case. Okay, type there is another way actually, which is through integration to calculate delta U and delta H. So the first way is the variable specific heat using the table. At temperature, we need only one property, which is the temperature. At this temperature, we can go to table A17 to A25 based on the given substance, then we can calculate delta U. But as we said, for each of those tables from A17 to A25, it is representing one substance. So from A17 to A25, it will be a kind of 9 substances, 9 gases. Air, O2, Na2, and some other gases. Only 9 gases. But if the working fluid is other gas other than the listed in tables from A17 to A25. Then in this case, we have another way to calculate the change of internal energy and the change of enthalpy by the integration of the equation. CV dt and Cv dt in this case. And in this case, actually in table A to C, you will find actually there is a given relation of a specific heat per kilomole. Actually, Cp bar is given actually as function of temperature equal to A plus Pt plus Ct square plus D multiplied by Tq. Okay, this function, if you have a specific heat, is function actually of different constant A, constant B, C, and D, and it is function of the temperature in this case. If you look at actually those constants, we can calculate all of this constant from table A to C. If you look at this table here, you will find here in this table, depending on the working fluid, we have list of substance, list of gases here. Depending on the type of the gas, we can get actually the constant A, B, C, and D. Then we can substitute in the specific heat relation to get the specific heat as function of temperature. And in this case, if you were to calculate the change actually of the enthalpy in this case, which is equal to H2 minus H1. It will equal to integration of Cv as function of temperature dt from T1 to T2. But the value, the equation given here is giving the specific heat in kilojoule per kilomole Kelvin, not per kilogram. That means this delta H I'm calculating is actually delta H per kilomole, and this specific heat actually is the molar specific heat. So it will equal to integration from temperature T1 to T2, A plus PT plus CT squared plus DT cube. This integration actually of delta T. Can you do this integration? It will equal to A multiplied by temperature plus PT squared divided by 2 plus T cube divided by 3 and plus D multiplied by T to the power 4 divided by 4. And then we have to actually substitute from T1 to T2 to calculate delta H in this case. Okay. Type this is delta H calculated in kilojoule again per kilomole. This is the molar value. Then to calculate delta H per kilogram, it will equal to delta H per kilomole divided by the molecular weight. And this molecular weight, as we said, is calculated from table A1 in this case. Okay. But this is regarding delta H. What about if I need to calculate delta U? So in this case, in this table A to C, you will find Cv is only given as function of temperature, but we don't have a relation for Cv. We said delta U is equal to integration of Cv, not Cv. So we have four gases here. I will prove this relation for you, just 5 minutes. Cv is equal to Cv minus the gas constant R. Okay? So the specific heat at constant volume for any gas equal to the specific heat at constant pressure minus the gas constant R. Okay? If we divide it by the molecular weight, so it will be, we can just Cv per kilomole equal to Cv per kilomole minus R bar, we call it R universal in this case. R universal, which is 8.314 kilojoule per kilomole. Okay? So in this case, based on this relation, then we can say Cv, the specific heat at constant volume, equal to Cv minus constant. And here we have constant. It will be A minus R bar, or R universal, plus PT plus CT squared plus D multiplied by T. And in this case, we can do the integration. So in this case, to calculate delta U per kilomole, will equal to integration of Cv per kilomole as function of temperature. This integration from T1 up to T2 in this case. And you can do this integration. It will A minus R bar, can just do it, plus BT C T squared plus D multiplied by T cube. This integration from T1 up to T2, integration dt. And the same, this is constant. It will be constant multiplied by temperature plus PT squared divided by 2, and so on. And then we can do this integration from T1 to T2 in this case. So the first way you have to calculate delta U and delta H is using table from A17 to A25. Okay, depending on the working fluid. If it is air, I will be using table A17. If it is oxygen, I will be using table A19, and so on. So we have 9 tables for 9 substances. But if the substance is not listed in those tables, if the gas is not listed in those tables, then in this case we can use the integration using the equation given in table A to C. And depending actually for a list of gases listed in this table, we can actually define the constant A, B, C, and D, and then we can do the integration to calculate delta U and delta H in this case. This equation, this second method actually based on integration, this is also still an accurate method. So the first one is the most accurate, variable specific heat based on the experiment. Second one based on the integration, which is still actually more accurate, or still actually it has high accuracy in this case. There is a third method, which we call actually constant specific heat approach. in which we assume actually the specific heat is constant, not function of temperature in this case. Okay. Type before I move to the third method here, delta U is calculated again. I have to write it in kilojoule per kilomole in this case. And to calculate delta U, it will equal to delta U per kilomole divided by the molecular weight. And this is the second method. Right, let's look at the third method. Okay, so the first method, variable specific heat, using table from A17 to A25. Second method, using the integration, using the equation listed given in table A to C. And the third method, yani, in this case, we'll be considering the constant specific heat approach. In this approach, we consider the specific heat as constant value, not function of temperature. We said delta U is equal to integration of CV as function of temperature dt from T1 to T2, and delta H integration from T1 to T2 CV as function of temperature delta T. We said CV and CV are function of temperature, but here actually we can have an assumption. If you look at the specific heat as function of temperature, using yani here is given, is a kind of second order equation or third order equation. Okay, like if this is a kind of representation here, the kind of second order. So if delta T for any gas undergoes this process, if delta T is small, okay, we have a small difference actually in delta T. Then in this case, we can assume this second order equation as linear in this case. And based on this, we can calculate actually, assume the specific heat as constant value, which we call it CV average value, calculated actually at average temperature, between temperature T1 and T2 in this case. So if delta T is small, we can assume linear relation. And based on this, actually, we can calculate average specific heat, CV and CV. And we can consider it actually as constant value in this case. Constant, we can take it here outside the integration in this case. So it will be CV multiplied by integration of delta T, which will equal to the temperature difference. And in this case, we can say delta U, which is U2 minus U1, will equal to CV average multiplied by delta T, which is T2 minus T1. And delta H, which is H2 minus H1 for gas undergo process from 1 to 2, will equal to CV average multiplied by T2 minus T1 in this case. And this is actually how we can calculate delta U and delta H based on the variable, based on the constant specific heat approach. Okay. Type how we can calculate CV average and CV average. We said this average value is calculated at average temperature, which is equal to T1 plus T2 over 2. And then we can calculate, take this average temperature and we go to table A to B. Table A to B, then we can calculate CV average, and we can get CV average depending on actually the type of the gas. So in the third method here, I'm using table A to B and table A to A bar. And I think table A to A can be used also in this case. I will show you. Okay. So using table A to B or table A to A, table A to A and table A to B, can get CV average and CV average depending on the gas. If T1 and T2 are given, we can calculate the average temperature and go to those tables to calculate CV average and CV average. Then we can say delta U will equal to CV average multiplied by delta T, and delta H will equal to CV delta T. This is a table A to B. In table A to B, you will find different gases. Here actually for the first table it is for air. Second table for carbon dioxide, and we have carbon monoxide. We have list of different gases, and for a range of temperature here, you will find the specific heat is given at constant temperature, and the value of CV is also given in this case. Okay, so I will calculate the average temperature. Let's say it is 400. I will go to table A to B. If the working fluid is air, then this is the value of CV, and this is the value of CV. If another working fluid, carbon dioxide, then actually this is CV. This is the value of CV, and this is the value of CV in this case. Table A to A, شباب, this is A to B. Table A to A, here is just giving the value of CV and CV, but temperature equal to 300, okay, for a range of gases. So if the gas is not listed in table A to B, in the table A to B, it gives you the CV and CV as function of temperature for a range of temperature, range of average temperature. But maybe you may not find the gas in table A to B. You don't have table for this gas. Like let's say if we have helium or something, we don't have table for helium in table A to B. Then in this case, we can use table A to A, but this table A to A is used only when the average temperature equal to 300. So it's very limited. But don't worry, طب in your exam, what should we do? Or when we come to testing you? So in this case, I will tell you in the exam either to use variable specific heat. Variable specific heat, that means the gas is listed in table from A17 to A25. And in this case, at the temperature, I can calculate the change of internal energy. I will tell you directly which method you have to consider to calculate delta U and delta H. But if I told you use the constant specific heat, then in this case you will say delta U is CV average delta T. Delta H is CV delta T. And this CV and CV average is calculated at the average temperature, and then from table A to B, most probably, because table A to A is only at average temperature equal to 300, and this is actually a very rare case. So I will be using table A to B to calculate CV and CV. Come here and substitute in the equation, then we can calculate delta U and delta H. So in the first law of thermodynamics, we have Q minus work is equal to delta U. If the working fluid is gas, then in this case I have to calculate delta U based on actually one of those three methods in this case. Okay. But I told you for the second way for the integration that CV or CV is equal to CV minus the gas constant R. I told you I will just prove it for you. Like for ideal gas شباب, for gas or for ideal gas, in this case we have PV is equal to RT, okay, and we have also the enthalpy is equal to the internal energy plus flow energy, which is PV. PV is equal to RT, so the enthalpy will equal to U plus RT, okay. Let's do the differentiation. So delta H will equal to delta U plus R constant multiplied by delta T. And by definition, we have defined delta H as CV dt, delta U as CV dt, plus R dt. So dt will go with dt, then we can say CV, the specific heat at constant temperature, will equal to CV, specific heat at constant volume, plus gas constant R in this case. Okay. We have another property for gas, which we call it the specific heat ratio, K, which is just the ratio between CB and CV. It's CB over CV. And this value, شباب, is listed in table A to B and A to A. You'll find K is given, CB is given, CV is given, and the value of K, which is just CB over CV, is given. In table A to B, you'll find also K is given, which is CB over CV in this case. Okay. So inshallah, you see here, شباب, the gas constant for some gases. For air, it is equal to 1.4. If we have actually for monotonic gases, single atom gases like helium, argon, it is equal to almost about one value. We can say it is almost fixed value, 1.667. And in case when we have actually polyatomic gases, more than one atom like C plus O2, it will be CO2. Unlike NH3 or any gas, it will be a kind of 1.33 in this case. Okay. So let's look here for this example. I will not be writing anymore in this case. And this example, you should have look here, just substitution for the three ways that we have considered. Here we have air at 300 Kelvin and 200 kilopascal is heated under constant pressure to 600 Kelvin. So T1 and T2 are given, pressure B1 and B2 are given. However, actually, we don't need the pressure. We said for gases, we can consider under low pressure, we can consider the gas an ideal gas, and in this case, the properties are function of the temperature only. We need only one property to use the table in this case for gases, which is the temperature. So we need to determine the change of internal energy using first table from A17 to A25, A17 for air. We need to calculate delta U, which is the most accurate one based on the experiment. Second, we need to do the integration based on the equation in table A to C. And the third actually is based on using actually the average or constant specific heat analysis based on the average specific heat in table A to B. Type here we are given T1 and T2. So for the first method, which is the variable specific heat approach, delta U will equal to U2 minus U1. And U1 is calculated from table A17 at temperature 300. You can check this value from table A17. This is table A17 for air, in this case, at temperature equal to 300. This is the temperature of 300, okay? Then we will give in here the enthalpy is given, the internal energy is given, and the entropy is given. This B relative is the relative pressure and relative specific volume applied for isentropic process. We'll be talking about them later on. But those are not actually reduced pressure and reduced specific volume, no. To calculate the compressibility factor, those are actually another parameter, So don't care about them right now, okay? So at temperature 300, I will actually go to the table, then we can get, this is actually the value of internal energy, 214.07 for the case of air at the temperature equal to 300, and this is the value. And also like this, we can get the internal energy at the other temperature, 600 Kelvin. Then we can calculate delta U. It will equal to this value. The other method, which is the integration, it will not come to your exam. I will not ask you, never ask you to do this. But this is another method. You will be using in your exam either the exact approach or the variable specific heat approach, or the last one, which is the constant specific heat approach. This integration is a kind of tedious mathematical job you can do. You can check for air from table A to C. You can get the constant A, B, C, D, and then CV will equal to CB minus the universal gas constant. So this is the equation. Do the integration, then you can get this value, okay? But this value is delta U per kilomole. So I have to divide by the molecular weight. This molecular weight we can get for air from table A1. Then will be actually this value delta U. It will equal to 222.5. This is compared to the accurate experimental value. It is very close. That means the integration is still actually is very accurate value. Type for the third method, which is the constant specific heat, I will calculate the average temperature. So average temperature will equal to T1 plus T2 divided by 2. T1 is 400, T2 is 600. T1 is 300 and T2 is 600, so the average will be 450. So at this average temperature, I will go to table A to B, and for air, in this case, I can look at the value, check this value, I can get the value of a specific heat at this temperature. It will equal 2.733 kilojoule per kilogram Kelvin. This is the specific heat. Multiply T2 minus T1, then we can calculate delta U. It will be equal to 220 kilojoule per kilogram, which is very close to actually to the value based on the experiment. That means actually our assumption when delta T is small, in this case actually we can use the variable the constant specific heat approach. We can assume CV as constant, and in this case the value calculated will also be accurate in this case. But for wider range of temperature, if the delta T is high, in this case, this error will be actually increased in this case. Okay. By this, I'm done about today. Let's inshallah continue next time. Okay.